Good morning, everyone. Hello, good morning.
Good morning, sir. Good morning, sir.
Okay,
Good morning, sir.
all right. You can just start.
Good morning, sir.
All right, all right.
Matthew said,
Yeah, and also, please, can you see my screen?
No, please.
You cannot see my screen.
Yeah,
Yeah, you cannot see
yeah,
us.
we do.
Can you see
I
it now?
do. Ibra, check your phone.
No,
Yes,
sir.
it is here, sir.
Okay.
Check your head. I see it here.
Are we good to go?
Me, I can't see his screen. Please.
You cannot see then. Oh, I don't know because I share the screen.
Yeah.
I've shared the screen. So maybe you
Yeah,
check
yeah,
your
yeah. I
screen.
can see it now. I can see it now.
Okay, okay. So let's continue.
Uh,
We go
Sir,
through
please, can
this.
you get video for our colleagues? It seems only 19 or 20 people
Only
have.
19. I did not have, haven't they connected? They should actually connect.
Yeah, some of us are having a network problem.
Okay, let's go.
Myself, my network is unstable.
No
So
problem. Let's
please
go.
record it.
Let's proceed. So we go to this
Okay.
section during our last meeting. Get it? And
Yes, sir.
we're able to solve the remaining the breakdown what potentials for the remaining gases.
Yes.
Okay. So that is Thomson's what breakdown mechanism. And there are some problems which actually relate to Townsend's breakdown mechanism, and these are the corresponding what problems. One, Townsend mechanism is that time lag of breakdown occurrence will be in the order of what 10 power minus 5 seconds, according to his what proposal. He actually came out with the conclusion that when a high electric field is subjected to a particular insulator, in such a way that the electric field exceeds the breakdown voltage of that insulator, like in terms of the gases medium. We are actually considering the what the gas medium. The breakdown what will actually take place within this period duration. Within 10 power what minus 5 seconds, the gas will undergo what a breakdown. However, experimental results from other researchers had found that the breakdown may occur at a very short time, which is what in the order of what 10 power minus 8 seconds. Those other scientists actually disproved his proposal based on what the time lag for breakdown. A very fast short time, a very fast short time lag of breakdown may occur when the gap is what subjected to a short duration or impulse voltage. Impulse voltage like what lightning strike. Do you get it? That's an impulse, a typical example of what an impulse voltage. Did you get it? The transient impulse voltage, example lightning, is a unidirectional voltage which rises to peak value very rapidly. Because the potentials in lightning is very what very huge. Do you get it? And it occurs at a sudden within a sudden period of time. Do you get it? Suddenly, it just occurs. Do you get it? So it can actually cause the voltage of the power system to rise to a peak value. Do you get it? And decay to zero at slower rate. The transient voltage study will be considered later. So we just deal with the lightning aspect in the preceding lectures. The impulse breakdown phenomena under transient voltage, especially breakdown in long air gap, cannot be explained by what Townsend mechanism. The impulse what breakdown system was not actually considered during what Townsend's what experimental experiment. Do you get it? As a result, around 1940, rather, these scientists actually what collaborated to propose a mechanism, another breakdown what mechanism called streamer theory or streamer what mechanism to explain the breakdown phenomenon caused by what the impulse. sudden impulse like lightning. This is what the streamer mechanism. Streamer breakdown theory considered three formation mechanisms, which are one, formation of what? An avalanche by what? Initiating electron by Townsend's first ionization coefficient. That's the primary process. And also a large local enhancement of the electric field by the ion space at the head of what? The avalanche. Large amount of what? Ionization of gas molecules in the space at the head of what? The avalanche. These are the what? The conditions which were actually used to formulate the streamer mechanisms. So this is the streamer mechanism. I'll just give you to you as what? A reading assignment. You can just proceed. Read something about what the streamer mechanism. Recovery of what? Electric field strength. Let's look at something. A particular dielectric like the gas, or it can be gas or what? Solid or what? A liquid has been subjected to what? A high electric field, which has finally landed into what? The insulating material losing its insulating property. That means the insulation have actually what? Undergone what? Breakdown. How can we actually recover the what? The insulation material? Usually, most of the times, some insulating materials like what? Gases, they do regain their insulation capabilities by turning off what? The electric field or the electric potential. You get it? When you do turn off the electric potential or the electric field, the ions, the molecules in the what? The gases, they do recombine. Do you get it? Form back the molecule. Do you get it? And when a particular time elapses, do you get it? When a particular time elapses, most of the what? The gases diffuses into the atmosphere. Do you get it? Thereby neutralizing the whole system, making the what? The gas to regain its dielectric strength. Do you get it? But most materials like what? Solid insulators, the solid and most liquid, after breakdown, when they undergo breakdown, there is no way they can regain their what? Insulating what? Material. You cannot reuse again. Do you get it? It undergoes what? Deterioration. There's no way you can reuse it again. It loses its insulating capability. Usually the current through an arc will be interrupted by switching off the voltage via circuit breaker or other switching devices. Immediately after this process, the gas remains ionized and is at high temperature. However, with time increase, a few tenths of what? Of milliseconds, the gas deionized due to what? The recombination. Do you get it? The gas ions, they do recombine. And when they recombine, it does what? It forms back what? The gaseous molecule. Do you get it? Due to recombination of electrons and positive ions and diffusion of what? Charged particles from the gaseous gap. In the absence of the charged particle, the gas regains its normal insulation strength. You get it? So the ability to recover their insulating property has made gases attractive for what? Insulator designers. In terms of gases, they do regain their what? Their insulating property. After what? Turning off the electric field. Do you get it? Solid cannot recover their what? Insulating characteristic. And liquid recover only after what? Necessary purification. In terms of liquid, during the what? Breakdown, other particles may be what? Present in the what? In the liquid, like bubbles, some metallic parts, and other aspects. So in terms of that one, and also water, because most of the times in terms of liquid, it undergoes what? Condensation and other stuff. Do you get it? Due to what? The heating effect. Do you get it? So there'll be traces of what? Water bubbles. So before the water can regain its what? The liquid can regain its insulating property unless you purify it by getting rid of what? Those dissolved substances. Do you get it? So after breakdown, a solid material needs to be what? Replaced by a new one. After breakdown, the solid material needs to be what? Replace the insulator. You need to replace in terms of solid. However, some new type of what? Solid material, such as what? Silicon rubber, they regain what? Regain back its insulating strength after having some relaxation period, especially within 2 to 3 days. Do you get it? Without subjecting what the same material to what the high electric field. Do you get it? Liquid insulator progressively deteriorate after each breakdown, as far as its dielectric strength is what concerned. So we are done with this slide. Let's continue with another one, and this one will be for. Let me see. There's a solid. Mm, let me check this and see. Okay. So we are done with the gas. I believe you can see my screen. Hello, can you see my screen?
Yes, sir.
Okay, so breakdown in
Yes.
what? Liquid. So in terms of the gas, the breakdown in gas. Any question? Do you have any question relating to what the breakdown in gases? Then let's continue. Look at something. This is the what? The laboratory test. This is how it is conducted. Whatever is here is what? A liquid. It can be oil. It can be transformer oil. Do you get it? And these are what? The electrode, the positive and negative electrode. They do connect the positive and negative electrodes to a high potential. Do you get a high electric field? It can be a voltage. Do you get it? So
Yeah.
actually what? Increase the what? The electric field, the electric potential. It will get to a point where you found this arc. Do you get it? And that voltage, you keep note of it. That means upon reaching that particular voltage, the gas, what? The medium, the what? The insulating material, which is the what? The liquid, undergoes what? Breakdown. Do you get it? So at that particular voltage, you get what? The breakdown voltage. That means when you are actually using that particular liquid or insulating material as an insulator, it shouldn't the what the high voltage equipment, the voltage being subjected to the high voltage equipment shouldn't exceed that breakdown voltage. It should be low. Do you get
Yeah,
it?
please, we can't hear
Below
you
the
clearly.
breakdown voltage. Do you get my point?
Yeah,
Yes.
we can't hear you clearly. The network is breaking. The
My
audio, your
network.
audio is breaking. Yeah. We don't know if it's the network or the software. The app. We are currently a breaking network, breaking audio.
The network is
Yeah, we are
breaking.
experiencing that. Yeah, we are experiencing audio, your audio.
My audio. Oh,
Yeah.
correction. Oh, hi.
I don't know if it's from your side or our side. Almost all of us.
Almost all of you.
Yes, please.
You cannot hear anything. I believe you can hear me now.
Yeah, we can hear you, but it's breaking.
Oh, okay. Don't worry. Let's continue. Practical insulating structure usually consists of combination of solid and liquid. Most of the times in terms of what? The insulations, we do use what? Two of them. We have the solid type, the liquid, and the what? The gas. Taking for instance a transformer, in terms of transformer, the windings. We do use what? Paper to insulate the windings. Afterwards, they what? Immerse what? The windings into what? An oil. So that means we'll be having what? Two insulators. Yeah, the liquid and the what? The solid. It can either be what? Solid and liquid or what? Gases. As we learn from what? The breakdown of gaseous mechanism. Formation electron of avalanche is responsible for a rapid growth of what? Current associated with what? The electrical failure of what? Gaseous media. But this is not what? The case for the liquid. In terms of the electron growth, which is the avalanche, it doesn't actually take place in what? In the liquid. Numerous what? Researchers have studied the breakdown of liquid and solid dielectrics for decades, for several years. Do you get it? But the findings and theories postulated by such researchers cannot be what? Reconciled. Produce acceptable general theories explaining what? the mechanisms. The state of what knowledge in this area is still very crude and inconclusive. A whole lot of what findings, experiments, research are still ongoing in relation to what the insulation what properties of what liquid dielectrics. Liquid dielectric, particularly hydrocarbons, are used in insulating media in high voltage equipment. You get it? We do use the oil immersed transformers. We have the oil immersed transformers, oil circuit breakers, power capacitors, resistors, inductors. You may find what liquid dielectrics in them. In comparison with what the gaseous dielectric, the liquid dielectric have what very high density. In terms of density, comparing what the liquid and what the gas, you know that liquid is what denser than what the gas is. In comparison with what the solid dielectric, the liquid dielectric fill the space to be insulated more easily. You get it? And also, moreover, liquid are better coolant and have self-arc quenching capabilities. Should an arc be set up in them? Do you get it? Then in terms of liquid, they do not actually serve as insulators. They have cooling what properties, especially when they are used in what high voltage equipment. So the liquid in what transformer oil, they serve two purposes. One for as a coolant, and another for what insulation, providing what insulation. So this is what a transformer, and these are a typical examples of what the transformer oil. This whole thing, the outer coverage is what the tank, and the tank is filled with what oil. The tank is filled with what oil, full of oil. This is the reservoir for the oil. You get it? And most of the times, the engineers they do actually check the breakdown capacity of the transformer oil. So they do take samples from this portion. They do take the oil samples and they actually run what the breakdown test subject to what the transformer, the potential being subjected to what the transformer. Let's say when it is what 33 kV, they just take a sample and they go to the lab and they subject a voltage exceeding what 33 kV to find out whether the liquid still maintains its what breakdown voltage. This is a typical example of what circuit breaker. A circuit breaker. This is the outdoor type. It's also filled with what oil. It applies to the indoor type, filled with oil. An example of what a paper what power cable. So this power cable, most of the times you can see there is a hole here, a hole here at the top. They do fill it with what oil. Most of the time it is what insulated with what paper. It can be paper. Paper is solid. Do you get it? Or what? Polymeric part like polythene and other stuffs. Do you get it? But most of the time they do add oil. They do impregnate it with what? Oil. Do you get it? So this is what? Oil filled power cable. Oil filled capacitor. In a typical application, liquid insulators are used less frequently than either gas and
Hello,
solid.
hello, sir.
Hello?
Hello, sir.
Yes?
Hello, sir.
Hello?
Please, like we are all trying to follow, but then the audio is not all that clear.
Not all that good. Okay, I'm recording. I'll just send you the audio. Maybe
Hello, sir.
I'm having what network difficulties.
The audio is not clear. We are trying to follow, but yes, please.
Okay, no, don't worry. I'm
Please.
having network problem. That's why. Don't worry. I'll just send you the audio, right? So just follow. Just follow.
All right. All right. All right.
There's what less significant activity in what liquid than what solids. This is largely because early studies allowed what reasonable models. So these are readings. You can just read. You can just read. Conduction process leading to what? Failure in what? Liquid dielectrics. Conduction process leading to what? Failure in what? Liquid dielectrics. They can be categorized into what? These processes. This is what process seen in what? Liquid. Movement of oil and particulate contamination, cavity formation, and chemical what? Reaction. Okay. In terms of the conduction process seen in what? Liquid, Conduction in liquid is largely by what? Ions. High field conduction may be through what? Electrons. All these are reading. So just read all these aspects. You can just read. You just get everything. In terms of what? The conduction, these were movement of oil and particles. They are categorized into these forms: dielectrophoresis, thermal convection, electroconvection, static electrification. Same applies to this part. Just read it. We are having a lot to do. We need to start working on the lightning phenomena and other stuff. A whole lot of calculations are there. So these are just reading. You can just read through. Done with what? The liquid dielectrics. Solid dielectric. Liquid. Let me see. Let me try this. Breakdown of fluid and what? Solid dielectric. As mentioned in what? The liquid section. Solids range from what? Crystalline materials to semi-crystalline. You can just read. In power system application, solid dielectrics mainly being used as indoor and outdoor. You can just read. So this is a typical example of what? A solid insulator, the paper, cardboard, insulating what? The primary and secondary windings of what? A transformer. So this is what paper insulating winding coil. A typical example for the solid. Do you get it? Polymers. Do you get it? A stress of what? Material. So in terms of the solid, they are categorized into three components. We are having the polymeric type, even more than three, it can be four. Even the wooden part. So many categories. We can use wood. You get it? And we can also use what? Paper. We can use the polymeric types, like the rubber types. And we can use what? All these are what? The polymeric type. A typical examples of what? The polymeric types. The polymeric what? Insulator are being used as what? A cross arm. There's it. We are having the what? The ceramic. This is what? A ceramic type. Do you get it? This is a typical example of what? The ceramic type being used as a pin insulator. A typical example of what? The ceramic type being used in transformers to isolate the primary and what? The secondary cables, conductors. Do you get it? The primary and secondary cables. Do you get it? All these are the polymeric types. The ceramic type. Typical examples of the ceramic type being used in what? The switchgears. All these are found in what? Substations. So insulators, in terms of insulators, they are very relevant. So a particular what? Substation, the voltage levels actually what? Differs. It differs from the whole it differs from what? The low voltage to what? The ultra voltages. Do you get it? So you should be able to calculate the insulation strength, the dielectric strength of all the insulating materials in order to know the required or the actual insulator to be used for a particular what? Substation. Do you got it? So you cannot actually use an insulator which can handle, let's say, 33 kV voltage or potential in a substation which is actually what? Rated at 66 kV. Do you get it? There's no way that insulator will be able to handle such an electric field. Do you get it? So it is most of the time it is desirable to determine what? The dielectric strength of what? Every insulator. Do you get it? So in terms of the engineers, they do consider all these factors. Do you get it? So that's why it is very relevant to know something about what? High voltage. All these are typical examples of what? The ceramic types. So they are employed in all the what? High voltage equipment. Do you get it? Transformers, generators, everything. All the high voltage equipment. Do you get it? So in terms of insulation, they play a major role in in power system. Do you get it? And we are also having about the glass type. This is a typical example of the glass type. And it can either be the pin type, the pin type. This is the pin type. For in terms of the polymeric, the pin type, this is the strain type, or the strength type. Do you get it? Along the lines. Do you get it? And this one, in terms of the pin type, it does sit on the what? On the ions, the channel ions. Do you get it? I saw a typical example. Something like this. This is the pin type. This sits on the ion, the channel ion. Do you get it? When those who have actually done the attachment in what ECG and other aspects, you should know what I'm trying to mean. And the strain types are used along the lines, along the transmission lines. Problem with what? Solid dielectrics. Upon breakdown in solid, the occurred damage is permanent and the insulator needs to be replaced with a new one. You get it? So this is the problem. But in terms of gases, when it undergoes what? Breakdown, what do you need to do? Quench the what? The electric field and it will regain its insulation material because the ions will recombine to form back the molecule. And most of the time, the ions, most of them will diffuse. But in terms of the solid dielectric, upon breakdown, there's no way it can regain its insulating capabilities. So in terms of that, you just get it off and you replace it with what? A new one. Under normal industrial condition, the same solid material are found to what? Exhibit a wide range of what? Dielectric strength, dependent upon the condition of the environment. Method of what? Testing. You can just read. Especially the dielectric strength. What this is trying to mean is that the dielectric strength of the same insulator at room temperature would differ from what? From what? That of what? The same insulator being used at what? A very high temperature. Do you get during the day? Do you get it? Because there will be what? Some chemical reactions and stresses going on there. Do you get it? So with the same insulating material based on what? The temperature. Do you get it? The dielectric strength may differ. Factors like temperature, humidity, type of voltage. Do you get it? Pressure. So if you're having the what? AC, DC, or input. Pressure, discharges in the surrounding medium, duration of test, influence the measured breakdown strength in solid material. So that's the explanation for this. You can just breakdown mechanism in what? Solid dielectric. The breakdown mechanism proposed as what? Okay, the breakdown mechanisms proposed are dependent on the time and of voltage application and may be classified as follows. The breakdown mechanism in what? In solid dielectrics. One being what? The intrinsic breakdown, electromechanical breakdown, thermal breakdown, in another aspect. You get it? So you can just read this aspect. There's what? Time and field of different failure mechanisms in solid. The time, the duration. This is what? The field. Do you get it? The field. 10 power what? 4 volts per centimeter. Per every centimeter of the insulator, of the what? Of the insulator. Do you get it? The training mechanism. Training mechanism is a chemical process. Do you get it? Within the field, let's say around 10 power 4 volt per centimeter, and the breakdown will occur within this time. Let's say 10 power minus 10 power 5 seconds. Do you get it? So the avalanche, 10 power minus 8 within a short period when it is subjected to what? 10 power 6 volts per what? Centimeter. Intrinsic breakdown. So you can just read this aspect. All these are reading. You just read to get ideas. You can read this aspect. So all these are given to you as what? A reading assignment. I'll just give you this as what? A reading assignment. Go through them. After prolonged operation. Clean. Breakdown in solid. Clean. Why the name clean? Look at something. The breakdown mechanism actually occurs in the solid material actually mimics what? The root of a tree. Are you saying this aspect? That's mimic the root of a tree. That's how come it is called what? Treeing. So you can just read all these aspects. So we start the main course next week. All these are just introduction. So I can say we are actually done with what? The breakdown in what? Mechanisms in the breakdown mechanism in what? Solid, liquid, and what? Gaseous dielectric.